Hello dear student friends, welcome to the experimental stress analysis class on photoelasticity, that is continued class of our previous class, okay, where we are discussing about the photoelasticity, module 3, nature of light, and those things, right? So in the previous session we were discussing about the what is photoelasticity, what is light, what is the nature of light, what is a polarization, what are all the types of polarization, and what are the methods of producing the polarization. These things were studied in the previous session. Okay, today we'll be moving on to the next concepts, that is what is the nature of light. We'll be looking at that again. Then what is the wave theory of light, and who gave the wave theory of a light. Then we will be discussing about those. Then what is the optical interference, then stress optic law, uh, how these plane stresses are being affected, and circular polarization or plane polariscope and circular polariscopes. We will be discussing how it will be affecting the model, that is when we get in between the light and the polarizer. Okay, then what are isoclinics and isochromatics? These are all the concepts we will be understanding. Okay, so nature of light, initially Huygens he attempted and gave us the concept of wave theory of light. Okay, in this he gave the light as a disturbance which travels in the form of the ether. Okay, then a scientist called Newton, he gave the light in the form of stream, which travels in the form of stream. Okay, then a major attempt to for giving the theory of light was by Maxwell. He gave in the 1816, okay, sorry, he gave in the year of 1859, who he represented the wave in the form of electromagnetic wave, right? Wave in the form of electromagnetic wave. We have also discussed about this in the previous class. Okay, how this electromagnetic wave have been classified, right? So as you can see in the figure, light has a electromagnetic wave. Okay, right, this is light has a electric field and a magnetic field which are perpendicular to each other. So this concept of light is given by our scientist Maxwell. Then before moving on to the another concepts, that is effect of a stressed model in a circular and a plane polariscope, we'll understand about the what is a wave plate and what is the importance of this. Okay, wave plate is nothing but it's an optical instrument or the element which enables us to resolve the light vector into two orthogonal components, and it helps in transmitting the those resolved components of light into different velocities, that is a slow axis and a fast axis velocity will be understanding. So the material which exhibits these wave plate properties, we call it as a double refracting or a birefringent material. Okay, as you can see in the figure, light will be resolved into two components, that is slow axis and the fast axis. Okay, right, so we'll be again understanding how this wave plate is be uh, resolving the components in the two vectors. Okay, here you can see plate is placed in the field of a plane polarized light. If you are taking up a plate that is placed in between the in a plane polarized light, Then when you take a wave plate, if you are placing in front of that, it will be resolving the components into two axes as we discussed earlier only, that is angle beta it will be giving. Then one of the axes will be having the magnitude of ET1 and ET2, right? So ET is nothing but the magnitude of the light vector that is traveling along the two components. Here ET1 is equal to ET cos beta, that is the beta is nothing but the angle between the two axes, that is fast axis and the slow axis. Okay. Then we will be resolving the components, as you can see, sine vector and a cos vector that we will be looking at. Then it will also have a phase shift between these two components, that is a delta 1 and a delta 2. H delta 1 is nothing but the h into n1 minus n, where delta 1 is the phase difference between the two components. H is nothing but the thickness of the plate that is taken for the analysis purpose. N1 is the refractive index of the stressed model, and n is the refractive index of the unstressed model. Okay, alright. Then we have a equation for the angular phase shift between these two components, and we will be denoting it as a delta, right? This is the equation for the relative angular phase difference. Okay, then we'll move on to the next concept, that is stress optic law. Okay, this gives the this is actually given by the scientist, that is Maxwell, in the year of 1853. Okay, here he gave us the equation for the fundamental relationship between the stress, strain, and also the optical effects. So this equation we call it as a stress optic law. Okay, so the main definition goes like this: the changes in the refractive index are directly proportional to the loads that are being applied on the component, and also the stress that are acting on the component linearly, right? So this equation we call it as a stress optic law equation. Okay, where n1 is the refractive index of the refractive indices of the principal stress in a different directions, n1, n2, n3, all three directions, x, y, and z direction. If you are taking up x, this is x, y, and z direction. Okay, these are the refractive indexes, and sigma 1, sigma 2, sigma 3 are the principal stress at different points in a x, y, and z direction. As we told, n naught is nothing but the refractive index of the material that has been unstressed state. Okay, C1, C2 are the stress optic constants, we usually denote it as. Okay, again I'll repeat what is stress optic law. It gives the relationship between the relationship between the refractive indices, and also with respect to that we will be deriving the relationship between the stresses at a different directions, right? So usually three equations, as we saw in the previous slide, there were three equations were denoted, that is in the 3D three-dimensional photoelasticity. As we are discussing about the 2D photoelasticity, so we'll be mainly concentrating on the x and the y direction. So in the z direction, stresses will be taking it as a 0, as it is limited to only 2D photoelasticity. N1 minus N0 is equal to C1 sigma 1. This is the equation for plane stress equations in the stress optic law. Okay, then we'll be moving on to the stress optic law in terms of relative retardation. These are the equations that will give us the relationship between the all the three directional stresses. Okay, these are the phase shift that are undergoing at a different phase due to change in the direction of the stresses. Okay, then we'll be moving on to the next concept, that is effect of stress model in a plane polariscope. So what is a plane polariscope or a plane polarization? Is nothing but the propagation of light in a one direction, either in a horizontal direction or a vertical direction. As you can see in the figure, right, when you are passing a ray of light through the polariscope, right, and here we are having a the component, photoelastic component, right, that is being stressed but when you pass a light through that, it will be resolving into two components, right, x and y direction, right. So when you pass this particular ray of light into analyzer, right, this initially when you pass the light through the polarizer, what happens, it restricts the light into propagate into one direction, and when you pass this particular ray of light into through model, so it will be dividing the light into two vectors. So that light, if you are passing again through the analyzer, what happens, if we are here we are rotating the analyzer, here we are having the polarizer in the perpendicular direction, and we are rotating the analyzer in the perpendicular to this polarization or this propagation. Here what happens, the ray of light will not be seen, no lights will be seen at the screen. So this process we call it as a dark field fringe arrangement, right, dark field fringe arrangement, right. So as we saw here, the principal stress direction, it is having an angle of alpha. So for that we have a magnitude, right, E py to k cos omega t, right. The same explanation. So at the end we will be having the equation as Ex is equal to k sin alpha cos alpha to a cos omega t minus delta 2. Delta 2 is nothing but the phase difference of the ray 2, and delta 1 is nothing but the phase difference of the ray 1. Will be understanding. Okay. So the final equation for the stress optic law is nothing but phase difference is directly proportional to the h is nothing but the thickness of the plate c is the velocity of light, sigma and sigma over the stresses in x and y direction, lambda is the wavelength. These are the certain parameters that on which a phase difference of that light will light which results into two components will be depending, right? So then we have a one more concept called effect of stress model in the circular polariscope, right? So the concept of dark field fringe will be seen here. Okay, effect of dark field fringe, right? When a photoelastic model is placed placed in the field of circular polariscope or in the pattern of circumference of a component. So this normal coincident that will go, right? When you pass a ray of light through the polarizer, right, so it makes the light to propagate in a one direction. Again, when you're passing the same light through the quarter wave plate, right, where quarter wave plate divides the light vectors into pi by 4 and pi by 4 angle or the phase difference. Delta is equal to phase difference, that is pi by 4. So it divides the two vectors into pi by 4 angle, and one will be having a very fast movement that we call it as fast axis and a slow axis. Again, when you pass this particular light, right, into on the stressed model, again it divides the component into the same light vectors will be falling on this again. So if you are taking up one more quarter wave plate, second quarter wave plate here, right, one more quarter wave plate, you are saying, again it will be dividing this particular component into pi by 4 and pi by 4. So this particular light, again if you are passing through the analyzer, where it again it is been rotated perpendicular to this initial polarizer. Okay, so again we will be seeing the dark fringe on the screen. So this arrangement of using these two quarter wave plates help us to get the circular polarization. Okay, here you can see how this circular polarization will be made. Okay, then effect of stresses in particular directions. Okay, as you can see, when you are having a alpha as 2 n pi by 2, where n might vary from 0, 1 to sin square to alpha. If you are taking up, then there will be extension occurring. So this above relation indicates that when the principal stress directions coincides with the axis of polarizer, the intensity of light will be 0. Okay, intensity of light will be 0, since as there are the analysis of optical effects produced by stressed model in a plane polariscope was conducted. It was arbitrarily conducted, and this particular experiment is valid for all the models. Okay, then we have a when initially we discussed when the phase difference is n pi. Now we'll be discussing when phase difference is pi by 2. What happens is sine square pi by 2, it will be sine square delta by 2. If you are taking up n as a 0, 1, 2, 3, etc. So the stress difference here either it will be 0 or it will be certain integer. Okay. So isoclinics, these are nothing but these are the light waves that are very sensitive to minima in light intensity. Okay, so the equation for the isoclinics can be given by this equation, right? So how these isoclinic lights waves are produced is by rotating the analyzer and the polarizer together. When you rotate it, isoclinics of various stress orientation can be produced. Okay. So in the coming up class we'll be understanding what are all the okay, or how these fringes are produced and how do we measure the fringe order, and also we'll be understanding how are these photoelastic models have been calibrated. Okay, thank you.